Okay, welcome everyone to day 4 of the Solution1 conference, hosted by the C# Community Discord. My name is Mike Treit. A little bit about me: I am a developer at Microsoft. I've actually been at the company for over 20 years, and a lot of the work that I do is on, at least for the last dozen years or so, is on sort of scalable web services. And as part of that, I've done a lot of multi-threading and like task-based code and async code and that kind of thing. And I thought that was a topic that when I talk to new developers, there's sometimes I find there's some confusion about the best way to actually approach doing things like multi-threading in .NET. And async is this really popular technique that people use, but I've also seen people misuse it. And this talk is going to go over some of the sort of details about how we do multi-threading and use tasks and all these features in .NET. So one of the reasons that using multi-threading and parallelism is so important is that hardware these days has lots of cores often available. If we look at, like, this is a screenshot of my home machine. I've got 48 logical processors to play with here. And if I'm writing my code in a way that is just purely single-threaded, start to bottom, there's very likely that I have lots of hardware capability that I'm not utilizing. So depending on the kind of programming I'm doing, it's entirely possible that I would be able to get much better performance if I took advantage of the multi-core sort of nature of the hardware that's available. Now, not everyone is running with 48 cores. Like my machine that I'm using here at my office only has 8 cores. But still, those are cores that we want to take advantage of if the type of programming problem that we're doing is sort of amenable to that. .NET provides a variety of options to help us with making code work in parallel on multiple processors. There's explicit threads, there's tasks, and there's also some helper methods that come through this task parallel library, which is where the tasks sort of come from. And we're going to look at all of these and show some examples of it. Let's take an example problem where we might be able to take advantage of parallelism. Let's say we need to populate a bunch of data. One simple example would be I've got multiple arrays in memory and I want to fill them with some kind of data. Maybe I'm loading data from disk, or maybe I'm fetching data from the network, and then we're going to do some sort of manipulation of that data. Here's the sort of straightforward, non-parallel way that you might do that. We've got basically some code here that is just, I have like a list of arrays. I want to fill each of them with some data. I'm just using a GUID in this example. Could be anything else. And we're just going to loop over each array. And then for each array, we're going to loop over each element, and we're going to populate that element with some data. Pretty straightforward, but this is purely sequential. It's all running on a single thread on one processor. And because we have multiple of these arrays, like let's say there's 8 arrays that we need to populate, there's no real reason that we can't actually, give one to each CPU core that's available and let each one of those do their own, so we can do all this data population in parallel. So here's how we might do this using threads. Now, threads are like the old school way of doing multi-threaded code in .NET. There was a time where the task parallel library didn't exist. And the way we used to do this was to use these thread objects. And this is an example of that. We've got an array of threads that we need to keep track of the threads that we create. And then we're going to go through and for that list of arrays, we're going to give each thread its own target array. It's then going inside the thread method, is going to go populate its target array with the data. Then we end up doing this thread.start. If you work with tasks at all, which you probably should be, and we'll talk about that in a second, You don't usually explicitly start a task. Tasks are kind of usually hot tasks. Threads are what we call cold. They don't start until you explicitly start them, so you have to do that. And then we keep track of them by putting them in an array, and then we end up doing this thread.join, which essentially just waits on each thread until that thread is completed. There we have the same thing, but using tasks. So tasks are an abstraction on top of threads that .NET provides. And they have a bunch of advantages over the old thread object. For one thing, tasks can return results. So we have like task of T, like task of string, might be a task that returns a string. Threads don't have any concept of like a return value. If you want to get a return value out of a thread, you have to somehow squirrel it out of the code somehow by maybe like setting a property on a class or a field or something along those lines. Tasks can return results directly, and then so that's a real advantage. Tasks can also propagate exceptions, which is not something that threads do in a way that you might expect. Let me actually give a quick demo of that. We have a simple program that all it is spawning a thread. This thread just happens to throw an exception, so we're simulating that the thread hit some kind of problem. And then we start the thread, we join on the thread, and we try to catch that exception. So if I run this guy, oh no, my program blew up. We didn't manage to catch the exception at all. And that's because, like I said, threads don't really have a way of, if an unhandled exception happens, that you have a way of handling that yourself. What you have to do is ensure that you catch the exception inside the thread, and then you can set that to a property or something and read it. So that's kind of a pain. If we look at the way this code works with tasks, except instead of starting a thread, we're using task.run to start a task. We have this, we're going to wait for the task to finish, and we have our exception handler. And if we run this, we'll see it's a little bit different. We're actually able to catch the exception, and that's a much better sort of programming model than the old thread way of doing it, where you have to do a bunch of shenanigans to try to, like I said, squirrel out the exception results so that you can see them. Tasks also make async programming, which is a topic we're going to go into a little bit later in this presentation, quite easy. None of the code in here is actually doing anything async in the actual tasks that we're running that are populating this data. Although you will see that this is a async method because we're using the async await mechanism just to wait for all the tasks to finish. So there's no async in the we spawned, but the outer code that is spawning those tasks could make use of async to not block itself while they're running. Also, we have these task parallel library helpers, and an example of that is this parallel for each method. So here we're doing the exact same array population thing, but we're calling this for each, parallel.forEach, and we're giving it the set of arrays, and it's then passing each target array into this body, and this may or may not run in parallel, but the intent is that it will. Parallel for each will figure out all the sort of scheduling and how many tasks to create. So instead of this code where we're explicitly creating n number of tasks and having to write all that code ourselves and make like an array to keep track of the tasks and then waiting on them, parallel for each just does all that for you. And I don't know about you, I would much rather write this kind of succinct, simple code than to write this kind of code if possible. And that's so one of the really nice features of the task parallel library is that we have things like parallel for each, parallel.for that do a lot of this work for us. So here's some benchmark results that we might find kind of interesting from the examples that we just gave. So this is the sequential time. That's 7 milliseconds in this particular scenario. We had 8 arrays, 10,000 elements each. The parallel tasks version, where we explicitly created tasks, did it in 1.7 milliseconds. Then we've got our parallel threads. And then again, we've got our parallel for each, which is pretty much on par with the parallel tasks. So one thing you'll notice here is that the parallel threads, while significantly better than doing it sequentially, was still not nearly as good as doing it with tasks. And the reason for that is that tasks make use of something called a thread pool. And the thread pool essentially has pre-created the threads and keeps them kind of warmed up and ready to process code if necessary. Whereas with the explicit creating of the threads, we have to pay the cost of creating threads instead of having them in a pool, and that cost is not entirely trivial. So clearly using tasks here is a win, and that's kind of the rule of thumb. When in doubt, use tasks. You almost never need to use explicit threads. As a matter of fact, Stephen Clary, who's kind of a well-known expert on the topic of concurrency in C#. As a matter of fact, I have his book right here, Concurrency in C# Cookbook, which is a great book. I highly recommend. Early on in this book, he has a statement that says to the effect, as soon as you type new thread, your code base is already legacy. You're already using old technology that you really shouldn't, because C# and .NET provide much better modern ways of doing it. And that's, of course, what this task concept that we're looking at is about. There are rare exceptions to this, however. So this is an example of some code that's part of a caching implementation that I worked on in the past. And you'll notice that it's using explicit threads. The reason for that actually is we were using a kind of a specialized internal serializer that was serializing data. And we were running in IIS, which is the Internet Information Server. It's the traditional Windows web server for serving web pages. And IIS has a very constrained stack size. By default, you get 256K of stack space for each thread, unlike, I think it's 1 megabyte is the default normally in other environments. And we were hitting a Stack Overflow. We were running out of stack space when we were serializing. And you'll notice that when we create our thread here, we actually have the ability to specify a stack size. .NET does not provide you this capability of increasing or decreasing the stack size for a given thread using tasks. So if you are in the rare scenario that you need to control the stack size on a thread, you can use an explicit thread object, and you have the control and the ability to increase the stack size, which is what we ended up doing in this code, and it solved the problem for us. So just be aware that there might be a situation like that where you would need to fall back to the old thread object, which other than this kind of thing, you should hardly ever need to use. Okay, there's another exception as well. If you want to have a dedicated thread that does not consume a thread pool thread and that runs for, like, say, the lifetime of your process, the way I would do that is to use this task creation options.long-running. So we can create a task using this task.factory.startNew. And you can pass this long running, and this essentially bypasses the thread pool. However, it is not guaranteed to bypass the thread pool. I think in reality it always does, but task creation options.long-running is documented as a hint. So in theory, the runtime may decide that even though you gave a hint that you want this to be a long-running thread, that maybe it knows better and that it's not going to actually use a dedicated thread. So if you 100% need to guarantee that you're not using a thread pool thread, you might need to use the old thread object. So we talked a little bit about the thread pool and how it avoids this expensive thread creation. The thread pool is really tuned for CPU-bound work. And as we're going to see in a demo I'm going to do a little bit later on, it really doesn't like to add new threads to the thread pool, which can sometimes cause problems. Let's do a quick demo. One thing when you're writing multi-threaded code is it's sometimes easy to get into situations where or things might not work the way you expect, or you'll get into thread safety issues, and that's one of the things I want to demonstrate here. So here's a simple program. We are just doing a parallel for loop with 8 things running in parallel. A parallel for is kind of like for each, except it's sort of like a traditional for loop. You give it a starting index, an exclusive ending index. It passes that index into your code, and then you can do whatever you want, but the body should run in parallel. In this case, we're just generating random numbers between 0 and 999. And we're using this random class here to do that. And every once in a while, we are printing to the screen. So if I were to run this, oops, forget that main thing, but that doesn't matter. There we go. We're generating these, we're printing them to the screen. Everything is working fine. So let's stop that. Now I'm going to make a tiny little subtle change to this code. So you see where we have this iters mod 2000 not equal to 0. We're going to make it equal to 0. And that essentially means we're going to be printing to the console less frequently. Before, any time it wasn't divisible by 2000, we were writing to the screen. Now we're doing the opposite. So let's run this again and see what happens. So here we go. We're going to start printing our random number. Oh, something doesn't look right. Suddenly all our random numbers have turned to 0. And that obviously would be a disaster if we actually need random numbers. And all we did was change this not equals 0 to equals 0. How the heck did that cause our random number generator to get completely corrupted? Well, the reason, of course, is that the random class in C# is not, or in .NET, is not thread safe. And thread safety issues are often very subtle. They rely on things like race conditions and timing. And just by changing the frequency at which we were doing I/O to the console alters the timing enough that we would actually hit this thread safety bug and end up corrupting the internal state of the random instance, and we hit this kind of a situation. But think of how insidious a bug that is. You could run this code for years and never hit this bug. Like, let's say it's this code is something that's running in your production service somewhere. You could be running fine and never hit this bug. And then let's say you upgrade your hardware. So now you're running on a slightly faster VM or that has slightly different performance characteristics. All of a sudden, this ticking time bomb that you had in your code the whole time will show up. And all of a sudden, your random numbers will be 0 or whatever. And all of a sudden, production will be broken. And tracking down this kind of a subtle race condition type timing bug is some of the hardest bugs that you'll ever have to actually track down. Sometimes these are called Heisenberg bugs, like they don't reproduce when you're looking for them. Like you might try to run this code forever on your machine, but it doesn't have the same timing characteristics of the machine that you're running up in the cloud, and you'll never be able to repro it. So this kind of thing happens actually not infrequently, and they're very hard to track down. So it's very important to be aware of them. This is another example of a classic bug that people make, a similar thing. We have a dictionary. We're populating the dictionary in a parallel loop. If we run this, it blows up because deep in the bowels of the dictionary code, it's trying to do a resize operation, and suddenly the destination array is not long enough because essentially you have threads stomping on this dictionary and it's trying to resize underneath the thread trying to write to it, and bad things happen. The answer to this is to use, well, there's a couple answers. One, you could use some kind of an explicit lock. Actually, in that, I have an example of that. If you know the lock keyword in C#, it essentially allows you to lock on an object And so usually what we end up doing is creating a dedicated object specifically to synchronize access to some piece of code. We lock on that, and then we do our random number call, and any other thread that's trying to go down the same code path is going to block until whatever other thread is currently holding the lock on this object releases it. So this would be one way to solve this. Also with random, there's in the latest .NET, there's a random.shared, which is a thread safe sort of global shared random instance. You can use that. Another option would be for each thread in here to create its own random instance. So you would have one random instance per thread. All of these are ways that you could solve this problem. So you want to be aware that those are the techniques that you want to use to avoid these kind of horrible thread safety issues, which can happen. Similarly, with something like this dictionary code, the best thing to do is to use something like concurrent dictionary, which is a thread safe collection that .NET provides. So if I switch to a concurrent dictionary and we run the same code, you'll see that it doesn't blow up. That's what it's supposed to do, and you're happy. So aware that if you are writing multi-threaded code, you should definitely be using thread safe collections, using locks, that kind of thing. And just to give one more sort of example of, oops, I think this one over here. This is another example of the kind of issues that that you see all the time when people write multi-threaded code, especially for the first time, and they're not quite thinking through all these sort of thread safety issues. Here's an example where I'm just spinning up a number of tasks. In this case, I'm spinning up 1,000 tasks. And we're incrementing this counter so that as each task finishes, we increment the counter. And if I go and run this, we should get the number 1,000, but instead we got the number 955. If I run this again, we'll probably get something else. In this case, 919. So, of course, the reason for this is that even something as simple as just incrementing an integer is not something that is entirely thread safe when you're doing it on multiple threads. Incrementing an integer is not an atomic operation. So when we do the little plus down here on total processed, it has to read the current value from some location in memory, probably on the heap, into some like CPU register, and then it increments that, and then it sets it back. But other threads are doing the same thing at the same time, and you end up losing data essentially. So the answer to this is to use something like interlocked class has an increment method, which allows you to say, and this is the safe way to do something like an integer increment. So if I save that and we run this again, we'll see that we've solved the problem. We get the right answer now, and life is good. So those are like a couple of examples of common thread safety issues that you want to be aware of as you're writing this kind of multi-threaded code. So always check if the data types you're using are thread safe. Use the lock keyword or one of the thread safe collections. The system.collections.concurrent has a bunch of them that solve a lot of these multi-threaded problems. Okay, here's another one that's kind of a subtle issue that I've seen in production. I've seen other people write this same bug, and it's actually the first time I ever encountered this. It sort of blew my mind. I didn't understand what was going on, and it took quite a bit of investigating to understand it. So here's a very simple piece of code. We are just doing a for loop. We're starting some tasks again, and the scenario here would be like I have this numbers array, and I want each thread to go like process a certain slot in that array. So here's our for loop. We are going to, inside each task, go take the index I was given and go do some work in that index of the array. So what is this going to print out? Well, let's run it and find out. So every task got the index 4. What's that all about? So this is an interesting thing having to do with the way closures work with lambda functions, which is what we have here. We have a lambda that we're giving to the task, and the index is out here, and we're using it inside the task. And so if you know the way that like this kind of thing works, it uses what's called a closure, meaning we close over the variable that we're accessing inside the lambda, and we capture it. And now it's available inside of this loop. But how come they all got the value 4? Like in this for loop, 4 isn't even a valid index into the array. In the for loop itself, if we ever accessed array of 4, it would give a out of bounds exception. So what's going on here? Well, the answer is that the variable I, when you have a closure and it captures something, it actually captures the variable. It doesn't capture the value, it captures the variable. And what is a variable? A variable is essentially a named memory location. You can think of it as, it's just an address that has a name. And so each one of these tasks is essentially given the same address. And this loop is just continually overriding the value in that address. And when this loop finishes, which it will finish quite quickly, and by the time the task scheduler actually schedules the task to run, at the end of this loop, the value is 4. That's the way for loops work. The last increment usually gets unobserved, but in this particular case, the for loop finishes, then the tasks get a chance slightly later to run, and now they're stuck with this memory location that has the value 4, which is absolutely not what we want. The solution to this is to simply do something like make a new local variable inside your loop. And if we use that and we run the code, we should see something different, which is that each thread or each task got the correct value. So this is a subtle error when you like use a for loop to start tasks, and knowing that you need to assign the loop counter if that's needed by the task to a local variable is one of these subtle gotchas that I've seen many times, and you definitely want to be aware of. So it's one of those subtle ones, but once you understand it, then you kind of understand why it works that way, and it makes sense. But be aware of that one. Okay, now let's talk about asynchronous code. Asynchronous code basically means that async essentially means I'll get back to you. Some work is going to go happen, and then eventually that work is going to come back and resume, possibly not on the same thread that it started on. And what that means is that the original thread is not blocked while this asynchronous operation is happening. We use async for operations that involve I/O, input-output, talking to disk, talking to the network. It's generally not the right choice for CPU-bound work. And I have this website that I'd like to show. Where's my browser? Why is that not coming up? Hello. All right, what's going on here? Okay, I guess I can't click the link while I'm in presentation mode. Anyway, here's what I wanted to show. And I've had this particular set of numbers over on my corkboard here that's in my office for years. It's something I sometimes refer to. I think every programmer should kind of know what these numbers are. The exact values are not as important as sort of the relative differences between the values. But essentially, we have two kinds of numbers here. We've got these numbers up here, and this is like CPU realm. This is work that the CPU does. interacting with memory, executing executing instructions, branch predictions, all this kind of thing. And these are all very fast, as you can see. We're talking single-digit nanoseconds, 25 nanoseconds, 100 nanoseconds. Then we have this stuff. This is the realm of I/O. And this is where things start getting slow, like reading sequential memory taking 250,000 nanoseconds. So generally, the rule of thumb is if you're doing stuff down in this region of the latency metrics, you want to be doing async. If you're doing stuff up here, you generally don't want to be doing async because this stuff is going to complete so fast that the cost of dealing with async is not really saving you anything by unblocking the thread because these times are very fast. So those are numbers that I think, ooh, where am I? Here we go. So those are things to be aware of, and there's a difference between when you want to use async and when you don't want to use async. We have a tag on the C# Discord that's the no thread tag, and it brings up a link to this article by Stephen Cleary, who I mentioned earlier, wrote this concurrency in C# cookbook and has a lot of blog posts on concurrency in C#. He has a great post explaining sort of the details about something that confuses a lot of people, which is that when you do async operations, at the time that the thing is async and is waiting for it to eventually complete, there's no thread involved. At the point that it goes async, it's not like somewhere there's a thread that's waiting for that to complete. The way the operating system actually implements this stuff is down at the hardware layers in the kernel, is that eventually there will be like a CPU interrupt or a device interrupt that comes back and something gets notified that ends up getting back into user mode, and then it can get scheduled to run on a thread. So it's a really good article. I highly recommend reading it. The way we do async and await is we use this async keyword. We say that this keyword is viral in nature because once you start using it, you essentially need to use it basically all the way down through your code. Oh, and on the previous slide, I mentioned all the async keyword does is enables the use of await inside a method. That's really all it does. It doesn't change the nature of the method. It just means you can use await inside of it. You will get a warning if you decorate a method with async and then don't use an await. So just be aware that that's really all it does. What await does is essentially allows the method to go async, go do some expensive I/O operation that's down in that sort of I/O section of those latency numbers we looked at, and then eventually continue potentially on a different thread. So one thing to note is that when you call an async method, it gives you back a task. All of the code inside that method until it encounters an await keyword is synchronous. So when you call an async method, and let's say you're going to call several of them and you want them to run in parallel or concurrently, you actually won't get that task back until all that synchronous code before the first await happens. And if that code is expensive, it can actually cause things to run a lot slower than you might expect. So that's an important thing to realize. And then once the thing goes async, the original thread that was calling is free to be used for some other work. And then eventually this continuation will happen, the code that's after the await, and that will happen potentially on a different thread. Await does not necessarily mean concurrent. This is a misconception that I've seen where people think like this first example up here where we have await, that somehow this is running stuff in parallel. And this isn't, right? Method B will never run until the await of method A completes. Then method B will run, and method C will run when that completes. These are all running basically sequentially. So if every time you're calling a async method, you're doing an await on it, you're not getting the benefits of actually running things concurrently. So if you want to be concurrent, you need to do something like this code here, which is assign the result to a task, and then you can, in parallel, await all of those tasks at once. So be aware that await doesn't mean concurrent, and if you want concurrency, you need to build a set of these and then use the task.whenAll, which is the right way to do that. Mixing async and sync. Don't. This is one of the biggest pitfalls that we've seen as async code has become a lot more popular. If you call these .result or .wait, the .result property or the .wait method, you're essentially making your code synchronous, which kind of defeats the whole point of async. It will tie up your thread, which basically defeats the purpose, and it can lead to deadlocks. So if you see in code something like get data async.result, this should be your reaction. That's not good. And if you see something like this write to cache async, and then you see this wait, this is also not good. You should alarm bells should be going off if you see code that's doing that. Let's do a little demo of that. Now, people who know me on the C# Discord know I don't know the first thing about UI programming, but I wrote one of the first UI programs I've ever written, basically for this demo. You'll be amazed at my my great UI design prowess. That's a joke. So let's take a look at a application. It's thinking about starting. Okay, here we go. And what this code does is I have a couple different ways of basically, if I click this, I'm just going to wait 50 milliseconds, and then I'm going to show a little message box. And I have a synchronous version. I have an asynchronous version. We've got this configure await one. I'm going to explain what that is. And then we've got this sync over async, which if I click, well, I'm dead. At this point, I've completely destroyed my program. There's nothing I can do with it. We have to kill it. So what's going on there is we did sync over async, the thing that I said you should get alarmed when you see. So that's the sync over async click. You can see we have a async method here, and we are doing the horrible thing that we shouldn't do, which is calling .result on it. And this is causing a deadlock. And the reason this is causing a deadlock is that if we go down and look at the code that's actually running, we have, I'm doing something async, I'm just doing an await, and then I'm just returning some string. But when we do await, it uses something called a synchronization context. And by default, it will capture whatever the current synchronization context is. And for most programs that are not something like a UI program like this, the synchronization context is just the thread pool. And so the synchronization context basically says, where should you continue once the await happens? And normally that would just be, okay, I'll continue on some thread pool thread, but that's not the way it works in UI programs. In UI programs, the synchronization context is essentially the main UI thread, and the code here, this return this string, when it needs to continue, it basically will try to continue on the UI thread. But what's the UI thread doing while it's trying to continue here? It's calling .result on this method. Well, I'm trying to return the result to the UI thread, but the UI thread is waiting for this method to return. And now we have this complete impasse. This is a classic deadlock, and that's the reason why when we click that button, this one over here, it's dead. It's the kiss of death, and we've completely blocked our UI thread, and at that point we can do nothing except kill the program. There is a solution to this. So if you're someone who's writing library code and somebody might consume your method and they might do the bad thing and call .result or .wait, there is a way that you can ensure that this deadlock problem doesn't happen, and that is to use this configure await method. We say configure await false. The false is this continue on captured context flag. And essentially what this means is that don't capture the current context, just use the default context, which will end up being the thread pool. And that solves the deadlock problem, which is why, if we go look at this again, so you'll see this code here is doing the evil.result thing that we normally shouldn't do, but because it's calling the version of this method that does configure await false, which is this button, you can see it works fine. We don't get the deadlock of death. So configure await false is something, especially if you're writing code where you don't control how it's going to be consumed, is something you should do. In fact, I was looking in our code base that I work on, how many uses of configure await false do we have? It's a lot. This I'm just grepping for configure await in our code base and measuring how many. Should be done soon. So yeah, 8,272 uses. Of course, I work on a fairly large code base, but in general, it's a good idea to use configure await false, even though it feels clunky. And I really wish the default behavior was the opposite. So you would opt into capturing the context instead of having to opt out of capturing the context. But that's a decision that was made a long time ago, and it is what it is. So, all right, that's my demo about sync over async and why you shouldn't do it. The other thing I want to point out is that async is not free. This is a misconception that I've come across with even some people I've worked with. Actually, my original sort of demo of this was based on talking to a colleague and finding out that he was using the async overloads on memory stream. And memory stream is up in the latency numbers. It's up in the green part. It's up in the pure CPU part because a memory stream is really a stream abstraction over an array in memory. There's no actual I/O that happens, and you're talking about memory accesses, which are in the like super low nanoseconds, and is not something where you would want to use async code. So here's some benchmark results that kind of show this. If you look, you'll see that we have reading from a memory stream, and then we have reading from a memory stream async, and it's essentially more than 3 times slower. Now, is it slow? I mean, we're talking things like, I don't know, 78 nanoseconds versus 27 nanoseconds. I mean, memory reads in general are pretty fast, but should you make your code 3 times slower for no reason at all? I mean, there's zero benefit to doing an async read of something like a memory stream. So I would contend no. Be aware that it's not free. There is overhead to using async, and that's because there is a bunch of machinery that I mean, the way async is implemented is using the state machine, and there's state transitions and stuff that gets allocated. And so you should be aware that it's not free. Another great example of this is I've actually written this code here, await task.completed task. So sometimes maybe in test code, or you decide that, oh, I don't actually need to go read this task. I just want to return to the caller this completed task that indicates, okay, everything's already done. If you do an await on this versus return, you're introducing a whole bunch of extra code and work. Can I go to SharpLab? Oh, this time clicking the link works. So if you were to look at, like, here's return task.completed task, what that compiles to is essentially this. It's basically 2 CPU instructions. If we go look at await task.completed task, which again is just a single line of C# code. I mean, how bad could it be? And you go look at all of the code that gets generated for that. Well, that's a lot more than 2 CPU instructions. And this is all of the stuff that gets generated to implement that async state machine, which if you actually go look at the lowered C# code, by the way, if you don't know SharpLab, SharpLab is one of the greatest sites there is. If you want to actually look at what's happening behind the scenes, like in this case, we're looking at the actual async state machine and how it transitions from different states and all this kind of stuff. If you really want to know what's going behind the scenes, SharpLab is fantastic, and I highly recommend using it. But that's just to give a flavor for, even though we only have like the difference between return task.completed task and await task.completed task. From the C# side, it seems like, well, what's the big deal? But obviously there's a ton of code that ends up And again, this is sort of the non-pessimization idea. Don't make the computer do more work than it needs to if you don't have to. And in fact, if you were to actually look at the benchmark numbers for returned completed task, I mean, it's a fraction of a nanosecond, and the await version is 16 nanoseconds. So obviously this is like 100 times faster. Just don't do more work than you need to. Again, 15 nanoseconds is not the end of the world, but why make your code slower if you don't have to? And that's the thing that I've tried to impress on people that I've worked with that have this impression that async makes your code faster. Async does not make your code faster. Async actually makes your code slower. Not necessarily a completely unbelievable amount of slowness, but it is making your code slightly slower. The reason that you do async is to free up precious resources like thread pool threads to do other work. It's not to speed up the code that you are running in an async manner. And that's where I want to do this other demo that is going to finally, I think, tie things together and show why async is so important. So I have a program that I'm going to run up in this upper window here. And what this program does is it creates 1,000 tasks. And what I can do is I can pass to this program a number that says, how big should the starting number of threads in the thread pool be? The thread pool has a concept of min threads and max threads. And max threads is kind of irrelevant because by default, it's like in 16 max value, it's like 32,000. So you never have that many actual threads. There's no real ceiling on how many threads could get created in the thread pool. But there is a sort of a lower floor, which is the minimum number of threads that it keeps warm in the thread pool. And by default, that number is set to the value for environment.processor count, which in my case is 8. And so the default value, if we run this program and I say, okay, use 8 for the number of processors, what's going to happen? Well, I'm going to spin up 1,000 tasks. And this program down in the bottom here, this guy is monitoring how many thread pool threads are running in the program up here. And so watch what happens if we run with the value 8. So this is using 8 for the number of thread pool threads, and you'll see something interesting happening is that the number of thread pool threads is slowly increasing. And it's increasing by about 1 every half second. So I said earlier that the thread pool really doesn't like to create new threads, and it really doesn't like to. It is very reluctant to add new threads because threads are expensive to create, and excess context switching can cause problems. So here we are. How long is it going to take to get to 1,000? It's going to take a long time, right? So even though I have these 1,000 tasks that, as far as I'm concerned in my code, have started, they're not actually getting CPU time scheduled to run. And if I press enter to signal them to complete, you'll see that we actually are logging here. How long did it take before the thread or before the task actually got scheduled some CPU time on a thread? And like in this case, it was 49 seconds. If we scroll up to the top, you'll see that some threads in here will have got scheduled pretty quick. Like here's one that only took 2.3 milliseconds. But that, of course, is because there were 8 threads in the thread pool. Any task that got lucky enough to run early enough that it could grab one of those threads, it got to start right away. But these others have to wait and wait and wait. And what this is thread pool exhaustion. And thread pool exhaustion is one of the most insidious things that can happen in a real world, like say production web service. If you run out of thread pool threads, all of those incoming calls, like let's say you're doing 10 calls per second, if you ever actually run out of thread pool threads, things just tip over and die. I mean, everything backs up. We've seen really crazy cases of this happening in our production services, where, for instance, in our logging, we can see, okay, this guy tried to open a connection to a SQL server, and the connection, that code finished 12 hours later because it did not get scheduled a thread to execute on for 12 hours because of thread pool exhaustion, and everything was backed up, and it was just, the poor system is trying to find threads to run stuff on, and because we had some sort of extreme like burst of events, bad things happen. And that's what this demo is showing, is that this is the burst scenario. This is like, oh, I'm running along, I'm processing requests, a few here, a few there, and all of a sudden I get this huge burst of requests. And I mean, 1,000 is a little bit of an extreme example, but that's kind of why I'm using it. Is it allows you to see kind of the worst case scenario, and obviously in this case, like, these tasks are not going to complete for hours. And in this case, the tasks are just basically sitting there simulating that they're off doing something. I'm using a reset event just to signal that, okay, now you can say you're done. Okay, so we say 8 obviously isn't enough. Well, let's give 100 minimum thread pool threads. Well, obviously this has the same problem, right? We're still going to sit there. The thread pool is going to slowly say, I don't want to add new threads, but okay, there's no threads available. I guess I will. And it will just keep going and going. But again, how long is this going to take to get to 1,000? It's going to take forever. So we could say, okay, well, let's bite the bullet and let's give, close to 1,000. Well, again, it's going to spin those up pretty quick, and then it's going to add a few, and then eventually we're going to have 1,000 running. So now all of our tasks are actually getting scheduled CPU time. But what happens if another 10 tasks come in? We have no thread pool threads available. So we're going to do the exact same thing and slowly spin up threads, and stuff's going to back up, and it's just going to be a disaster. And you can see here that time, most of the tasks got scheduled pretty quick, 300 milliseconds. That's not terrible. And then there were a few that probably took longer, because like this one took 3 seconds because of I didn't exactly put 1,000, I put 995. But you can see what a problem this is if you are occupying your thread pool threads while you are processing requests. So if you're writing some kind of a server and a request comes in and you're blocking that thread pool thread, you can run out, especially if you're using something like the default min threads, which is only the number of processors available. So how do we solve this? Well, this is why you use async. You don't use async to make your code faster. You use async to solve this problem. So I have another version of this, which if I run with the async keyword, is instead of blocking the thread, it's going to go async. It's going to still be off simulating that it's doing work, and it's still waiting for me to press enter to signal that, okay, you're done now. But it's going to do it using async and await. It's going to call await on the, it's now using a async manual reset event to sort of simulate this I'm off doing IO thing. So watch what happens when we run this. Okay, we've kicked off our 1,000 tasks and 0 running thread pool threads. Life is great. At this point, we've got 1,000 tasks. They're all off doing work. They're all off doing IO or whatever. But if other requests come in, we've got, well, I gave it 995 minimum thread pool threads. So we've got way more thread pool threads than we need, and they can service those requests. And if those requests also use async, that thread will immediately get returned to the pool. Remember the Stephen Clary no thread blog post, which you should definitely read. This is what it's talking about. I am not using any threads right now. I mean, zero thread pool threads. And yet we have 1,000 tasks in flight. And if I signal them to complete by pressing enter, you'll see they all complete right away. And look at the start delay for all of those tasks. It was basically nothing. So I hope this hammers home the reason the async await is so important is if you are doing things where you have to do IO, if you're doing things where you're in that lower quadrant of those latency numbers that we looked at in the numbers everyone should know, you absolutely should be using async. It frees your thread pool threads to go do other work, or it frees your UI thread, for instance, if you're doing UI. So it can process other UI events and you don't have UI glitches. It's just an extremely important technique to know, but you need to know to use it right. And like I said, don't use it on something like a memory stream. Another example that we have from my own work is sometimes you have to be judicious. Like, I want to go get 1 million rows from a SQL server. I want the initial connection, the initial, say, stored procedure call to be async, but I don't necessarily want to call the async read method on every row because my goal is to get that data out of the server as fast as possible so that I can serve it to my customer that's making the call as fast as possible. And doing async on every row actually ends up being counterproductive. So there's a lot of balance there where you have to sort of weigh the pros and the cons. Another example of that is this whole minimum thread pool threads thing. Like, if we go back and we rerun the async version of this program, and we only use the 8 thread pool threads, again, there's 0 thread pool threads running, right? Life is good. But what happens if all of those 1,000 tasks complete at the same time, which they're going to, because that's the way I wrote this program. When I press enter and say, okay, you guys are done, it's going to take a long time to actually finish all of them because all of those continuations need to be scheduled on a thread pool thread, and we've only got 8 of them right now. And so there's a balance there too, where sometimes you do want to do things like raise the floor of your minimum thread pool threads, but this is the kind of thing that really, you have to be the expert on the kind of code that you're writing and whether or not that's a scenario for you where you would have like a large burst of things. So this took 25 seconds instead of essentially being instant. So that's just another thing to be aware of and something to consider. We're almost at the top of the hour. That was pretty much all the content I had. So I think we can probably go over and do Q&A. So I'm going to go look on the Discord. And I will be looking at the chat for any questions. Okay, question. Is there any real interest in using async in a single-threaded console program or for an ASP.NET program? It's easy to see the issue with sync calls on a GUI program where the UI becomes unresponsive, but it's way harder to see the benefit for console or ASP. Well, definitely in ASP.NET, you want to be using async for exactly the reason that I showed. If you're doing I/O, an ASP.NET request comes in, that's going to be executing on a thread pool thread. And you want to free up that thread pool thread to process other requests if that's happening. So console application depends on what it's doing. If it's a single threaded console app that's just reading like from a file at startup, I would definitely not use async for that. You're not trying to like free up thread pool threads to do other work if it's just a simple console application. So Brainiac asks, question, we're storing a bunch of tasks in this array so we can wait for them with task.winAll. My question is, when you're storing, does it immediately runs or does it get run when winAll is called? No, the tasks are already running. Like if you don't call winAll, the tasks are still running in the background. And by the time you actually call winAll, it's entirely possible that they will have already completed. So as soon as you call the method, the task will get created and will start running. Like I said, the synchronous code actually runs first, and then it goes async when it hits the first await. Trace asks, what do you think about some people returning the task directly as opposed to awaiting when they call a single async task method? In my opinion, it's not worth messing up the call stack for the small performance gain. It depends on if you have other work that you need to do while it's running in parallel. Like await is, okay, I don't have anything else to do here. Let me wait for this thing to run, and then I'm going to continue on with the other stuff I need to do. But very often we might want to run things in parallel. So like, let's say I'm going to make 2 calls to a SQL database, which is kind of like the stuff I work on, right? That's how I think about it because that's the kind of thing I'm writing that kind of code all day. We do what's called fan out, where we often fan out to sharded databases. And so I might want to go query, say, 16 databases in parallel. And if I'm doing that with await, it's like, go query this database. Okay, await that. Now query this one. Await that. It's going to be serialized when I could get the benefit of running all that stuff in parallel, going async, letting the async IO happen, but now happening concurrently, and then we get the results back much faster. So it really depends on your scenario. Let's see. Are you going to show volatile? Where should I use this? I didn't show volatile. I actually thought about it. Generally, you shouldn't use volatile. Volatile is a very, I have mail threads with people who are way more experts from the .NET team on me about when you should use volatile, and I still don't understand when you should use it. Volatile essentially forces the CPU to not reorder reads and writes, which in very specific scenarios can make a difference, but it doesn't affect atomicity. So like using volatile does not suddenly make your writes or your reads atomic. Like when we were showing the counter increment gets screwed up because we were doing it in a multi-threaded, like volatile doesn't help with that at all. There are scenarios where it helps. Jeffrey Richter in I have his book, The CLR Review of C#, he has a example implementation of double check locking, which is a common pattern that I've used many times. I generally don't recommend it anymore. I think it's better to use something like lazy of T. But he has an example of double check locking where he shows that you need to use volatile, and if you don't use volatile, your double check locking is wrong on certain architectures. And when I read that, it blew my mind because I've been writing the double check locking pattern without using volatile for years. And anyway, volatile is kind of a interesting topic. One I don't claim to understand, but it's very rare that you should actually need it. But yeah, it's a great question. Should a lock be used with concurrent dictionary? No. Using a lock with concurrent dictionary basically defeats the whole purpose of using concurrent dictionary. Concurrent dictionary, it actually uses some lock-free stuff internally, which actually makes the performance even better than using a lock. But that's the whole point, is that you shouldn't need to use lock if you on concurrent data structures, they do all that internally for you. So yeah, don't do that. Is there any usage for barriers, mutexes, and semaphores with tasks? Yes, I mean, like a counting semaphore, for instance, is designed to, like, I only want to let n things happen at once. Like maybe I know that I have a limited number of resources, so I could spin up 100 tasks, but I might want to only allow 10 of them to actually go access these other 10 things at the same time. And there's all sorts of reasons that might be for performance. Like I don't want too much concurrency. I'm trying to limit the amount of CPU, like in this scenario, like I'm doing a background work. So that would be an instance where you might want to use a semaphore. Same thing with mutexes, like that example I just gave where I had 1,000 tasks and they're all like waiting to be signaled to be done. That's the kind of thing that you can use. Well, actually, like a manual reset event is what I was using in that case. All the classic threading synchronization primitives like mutexes and semaphores and reset events, they all apply to tasks just as much as they used to apply to multi-threading code. There are scenarios where you want to, like, okay, block all the threads for a bit, and tasks are just using threads, right? And then do something else and then release them. And so all those kind of scenarios can absolutely be a thing with tasks. Let's see. Any other questions? Question, in the serializer stack size example, would it make sense to build a custom TP? I'm not sure what that's referring to, with stack size configured threads. Maybe. Like in our case, we're just explicitly spinning up a thread, and that solved the problem that we had. Thread pool, I guess TP probably means thread pool. So building a custom thread pool is not the kind of thing that I would want to do, but I think, yeah, that's definitely maybe something that if you had a very specific scenario, you could think about doing. To be honest, though, if you are worried about stack size, like you're actually stack overflowing and you have to increase your stack size to avoid stack overflowing, you're probably doing something wrong. Our case, that we were using this very specialized serializer that in a constrained 256 kilobytes of stack space memory situation. In our case, it made sense, but I generally think that when you have things like stack overflows happening, and often that's because you're doing something like recursion, which you shouldn't usually do in C# in like a production scenario if you don't have a very clear constraint on the depth of recursion, because then you'll stack overflow, and I've seen that bug in production myself. Usually stack overflows are a sign that maybe you should rethink the way that that code is working, but yeah. A custom thread pool could potentially be a way of solving that. Question, is there guidance for observability of threads in something like Grafana or App Insights to understand how the app is operating? Yes, things like App Insights and like the Grafana dashboard views on your services and things like Azure. There are performance counters for things like, as far as I know, actually, I don't know about thread. I mean, we have memory, we have CPU. Certainly in Windows, traditionally, we use performance counters for things like looking at threads. I'd have to go look for the cloud dashboard. I haven't actually gone looking for that information specifically. In our services, we log some of that information. Like at the start of every request, we say, here's how many thread pool threads are actually executing right now, so we can go see if we're ever coming close to thread pool exhaustion. That's a good question. I'm actually not sure. A lot of questions here. Question, are there ever cases where you might run a task inside a thread or vice versa? Yeah, you could, sure. There's absolutely no reason you couldn't do that. If for some, like, let's say I'm running a task, or let's say I need that stack space thing for whatever reason, or I really want to guarantee that I have some background thread that runs for the whole life of the process, I could explicitly spin up a thread. There's nothing wrong with that. And inside that thread, I could spin up tasks. And certainly inside a task, I can spin up threads. There's no reason you couldn't do that. Question, I like this terminal multiplexer. What are you using? I am just using Windows Terminal. And this is my Windows Terminal. I use it all day long. I'm a command line guy, so I sit in the terminal all day long, and I have a bunch of different profiles. And Windows Terminal is absolutely fantastic. Windows Terminal supports panes, so if I wanted to split panes, I can split a pane, pick a profile, and then I'm going to do some Rust programming. I don't know, split that down, right? You know, that's the sort of the terminal stuff that I'm using. So, okay. I heard .NET is looking into implementing green threads. Yes, I've seen David Fowler tweet about that. What's the difference between how the CLR handles virtual threads and how the operating system handles it? If it would be implemented, that's a good question. I don't know. Technically, .NET threads, even the ones that we're looking at today, are a abstraction on top of the operating system threads. There's a reason why you would look at something like, it's called managed thread ID, like environment.current managed thread ID. I think that's something. Let me see here. Oops. Environment dot current managed thread ID. Yeah, so the reason this says managed thread ID is there's not necessarily a direct mapping between the OS thread and the managed thread, and so there's some abstractions on top of that .NET implements. Exactly how those work is a level of detail that I've never delved into, so I'm not sure. And the way it would work with green threads, I mean, green threads are not really threads at all, right? They're cooperative multitasking, is my understanding, where, you know, I'm sort of choosing to yield to something else to be able to execute, and then it comes back to me. It's like a coroutine kind of a thing. But I've never worked with green threads, so I don't know too much about them. It would be interesting to see what they bring to the table. Question, how do you call synchronously an async method when you can't make your code async all the way down? That's a good question. Essentially, you end up doing the evil thing that you shouldn't do, which is you eventually call .result or .wait. And hopefully the async code you're calling does configure await false, and you don't get into situations like deadlocks. So when you have a mixed not async all the way down, eventually you're going to have to do the thing that I said you should never do, which is why, if at all possible, you want to make your code async all the way down. Is it urban legend that after a certain portion of time, a task.run call will get promoted out of the thread pool, just as if you use long running? I don't believe that's a thing. I don't think so. I don't know where that comes from, but I've never seen that sort of behavior. I don't think that's a thing. I could be wrong though. I'm not positive about that. If you are starting tasks that run that long, you probably should use the long running flag. Question, is it typical to use a semaphore to lock when the context is async? No, I don't think that's typical. I've never used a semaphore in that way. If I needed to do a lock in an async method, I would just use a lock. Of course, that's going to be code that's executing synchronously. So I'm not quite sure what the idea is there. Question, I know that you are a benchmark lover. How would you benchmark a program using TPL versus one not? I mean, I've done a lot of benchmarks showing using tasks, using parallel. I mean, I showed benchmark results. I'm not sure if you mean like actually making the benchmark somehow run in parallel. That's not something I've ever tried, but certainly I benchmark code that uses the task parallel library all the time. Question, can we say that you like TPL and async a lot? Or should we say that you love that subject a lot? Oh my God. Yes, that's dollar a lot, and read that. Question, when is scheduled session on TPL data flow? You know, so Stephen Cleary in this book has a whole section on data flow, and I've never used it. I don't know anything about data flow. I've never known the use case for it. I've always just written basic task stuff, and you know, maybe other things. If I need a producer consumer model, I use something like blocking collection. I know there's like pipes and stuff you can use for that now, but I don't know anything about data flow. So if someone else wants to do a talk on that, I would like to watch that talk myself. Question, how do you call synchronously and asynchronous? Sorry, that's a response. Why not get awaiter, get result to get the proper exception? I mean, get awaiter, get result versus dot result is a thing that people debate about. I never call get awaiter dot get result, but I also try to avoid calling dot result anyway. Question, resources for continued research. Research on what? I'm not sure what that's referring to. I guess meaning if you want to know more about concurrency in .NET, I highly recommend the Stephen Cleary book, and any blog post by him or by Stephen Tobe are really good resources on this topic. Let's see. Teb is talking about agent-oriented buffer, pipe, sync flow, max degrees of parallelism. That all sounds interesting. I don't know too much about it, so I would love to know more. Build off this question. If you're limited to using async and cannot bubble async all the way to the top, what do you think about switching to events to avoid using dot result and the like? Yeah, that's possible. Event-based programming definitely has its purpose, so that might be something that would help with that. We've got, I think, 2 more minutes, and so any other questions I can answer before we wrap this thing up? I am not seeing any more. I'll wait. Just I see a bunch of people typing, so we'll see if there's maybe one more question in there, and if not, we'll go ahead and call it. All right, well, I think I'm going to go ahead and wrap it up. I will hang out on the chat on the Discord if people have other questions. And thanks very much. Thanks again also to Brainiac, especially for organizing this whole thing. I hope people got something out of this talk, and it was really fun. So thanks a lot.